Okay, so today, I think this is maybe the last lecture that we're going to do specific on trusses, actually. We only spent a week on trusses. It's sad. I kind of like them, so oh well. But we have other fish to fry. We have other interesting things we have to get to. Next week, we're going to start on beams, and that gets a little bit more complicated, so we have to reserve time for that. But trusses, we'll kind of give trusses their last hurrah, as it were in today's lecture. We'll be talking about the subject of stability, structural stability. And we're talking about it in the context of trusses, but everything that I'm going to present in today's lecture actually is relevant to stability of structures more generally and some of the issues that you might face in not just setting up and solving these problems by hand or even using these kind of MATLAB codes that I'm giving to you. These are issues that you kind of have to have some awareness of, even when you're using commercial software tools like ANSYS or SAP 2000, a bunch of other things. That in the background lurking here, you can kind of see some of these error messages. And these are examples of some of the messages you might receive if you run up against some of these problems. So we'll kind of give an opportunity to showcase some of those things. But to really motivate things, let's start off with an example. Again, we're going to build off of that MATLAB script, the one that you're going to be using for homework assignment number 3, I believe it is, in implementing this two-dimensional or three-dimensional truss program. And there's a bunch of these predefined problems that I put into that script that you can kind of test out and run and verify that your implementation is correct and just explore different problem setups and things like that. And among them, you'll find this one, the so-called ill-constrained problem, which is a simple truss that has these interesting support conditions as shown here. There's really only 2 constraints. I'm constraining this node in the x direction, and I'm constraining this node in the y direction. And probably from the outset, you can tell that this is the name says it all. What's wrong with this? What's wrong with this problem?
Needs to be constrained.
Yeah, we need some other constraint. It could be here where we're constraining vertical displacement. We could pick some other joint and constrain it in the vertical direction. But importantly, as you point out, this problem is not constrained against rigid motion. If we were to let it go, what do you think it would do? Just like, yeah, it basically, this point would want to move down, perhaps, there's nothing constraining it from doing that. This point could move left or right, and in general, the whole thing is probably going to rotate or something like that. So rigidly rotate, where this joint is displacing downwards and maybe this joint's moving to the left or something like that. So that's kind of what we expect to see. Now the question is, what do you think MATLAB is going to do when we try to run this problem? It's going to not run at all, probably. I mean, that's kind of what we would hope. If we were trying to solve this problem by hand, we'd run into that problem of a stiffness matrix that really couldn't be inverted. That's kind of what we expect to see. And we expect MATLAB is going to encounter that same problem. So what happens? Well, we run MATLAB, and interestingly, we do actually get some results that are displayed here. And interestingly also, the displaced shape of this structure actually looks intuitively like what we would expect it should look like, right? It's doing this sort of rigid rotation. The weird thing, though, is that the internal forces are sort of, I don't know, maybe these are small to within machine precision. I mean, this is only like 20 newtons. So perhaps this is just numerical noise, but it looks totally random and weird. But still, the question remains, well, can we really trust these results? And how exactly did MATLAB come about getting these answers if we knew ahead of time that really this is an ill-constrained problem? So what do you suspect is going wrong, just kind of based on your intuition? How did MATLAB get this? Oh, well, yeah, that's what we're going to try to find out. Well, we'll see. So we'll actually see that, maybe this is not so far away from what we expect to see, but MATLAB is sort of tricking us into giving us an answer. It's doing the best it can to give us an answer, even if it isn't necessarily the unique answer to, a well-posed boundary value problem. So this is kind of why early on in the class I was telling you it's important to distinguish what constitutes a well-posed boundary value problem. you yourself have to make that determination and ensure that you're setting up a problem that has a unique solution. Otherwise, you could be setting up an ill-posed problem and you'll be getting an answer, but it might not necessarily be the answer that you're seeking. So just kind of bearing those details in mind. Okay, so let's actually take a step back, all the way back to statics, and take a look at this particular problem in the context of some simple heuristics that you might have seen either in your statics class or strength of materials, or maybe even as recently as your structural analysis class or what have you. If we're looking at a truss structure, there's a simple heuristic that you can use to try to estimate whether or not a structure is stable or not. And the simple check that you do is to determine on the left-hand side of this inequality, the total number of elements or members in your structure plus the total number of constraints. And nominally, if you're solving, let's say, for the internal forces in a truss structure using basic methods of statics, then technically these are representative of the total number of solution unknowns that you're solving for in a statically determinate type of truss. So the total number of elements, it corresponds to the total number of internal forces in the structure, or unknowns, if you like, plus the total number of constraints, which corresponds to the number of reaction forces that you also have to solve for. So if your unknowns are represented as internal forces and external support reactions, then technically this left-hand side can be interpreted as the number of unknowns that you're solving for. On the right-hand side is the number of dimensions in your problem, or the number of degrees of freedom per node, times the total number of nodes, or the number of joints in this case. And really, on this right-hand side of the expression, you could interpret this as the number of equations that you have to work with, the number of equilibrium equations that you would be solving in order to determine these kind of sets of unknowns that you're solving for. And it turns out in the case of an unstable truss, you'll find that if you tallied up both of those things, that if you found that the total number of elements plus the number of constraints was less than the number of equilibrium equations you had, then you'd find the structure was unstable. And that was kind of a nice heuristic you could use. If they were equal to each other, or in other words, if the number of unknowns in this problem for a statically determinate truss equals the total number of equilibrium equations that you're working with, then there's enough equations you can use to uniquely solve for all those unknowns. And that was suitable for solving trusses in this statically determinate context, maybe by the method of joints or what have you. If you had more of these kind of internal force-based unknowns in your structure or constraints, then you had equilibrium equations. Then we said in statics and whatnot that you had a stable structure, but it was statically indeterminate. So you couldn't necessarily use method of joints alone to solve for all those different unknowns. But now, I want you to reflect on how this contrasts with some of the equations that we're setting up and solving in the context of this finite element method. A lot of the trusses I've been showing you have been statically determinate trusses. So we could theoretically analyze them and intuitively try to rationalize how the forces should distribute. But technically speaking, the methods we developed are perfectly applicable even in the case of solving statically indeterminate structures. And that's because we proportion the number of unknowns we're solving for, the displacements at the joints, to be equal to always the number of equations that we have. So we're always able to solve for the displacements or the unknowns of the structure, and it's more of a post-processing step that we use to go back and find what those internal forces are. So that's the other kind of advantage, maybe subtle thing that you might not have kind of realized, that really in developing this whole kind of matrix-based approach to solving these systems of equations and treating the primary unknowns as being the displacements, that crucially enables us to solve even statically indeterminate problems. Now, still, it's useful to use this heuristic nonetheless to assess, whether or not you have an unstable structure. So let's actually go ahead and apply that to this particular problem that we were looking at a moment ago and count up how many elements do we have in the structure, in this case 11, how many constraints do we have, or how many supports, in other words, just 2 in this case. Obviously, it's a 2-dimensional problem, so there's 2 degrees of freedom per node, or 2 equilibrium equations per node, and a total of 7 nodes. So if we tally this up, the number of unknowns in our problem on the left-hand side is 13. On the right-hand side, number of equations is 14. So it ends up being the case that indeed we estimate this is an unstable structure. That might be helpful for you in homework assignment number 3. There's a particular problem that explores the issue of structural stability. So, this might be a good way to check and verify what's going on in that problem. Okay, so that makes good sense. All right, so this one should have been unstable. We should have known that ahead of time. And you could rationalize that intuitively, or you could kind of apply this heuristic to kind of determine it. Now, the other thing that I want to point out that I didn't show when I was showing you the results of this particular problem, when we ran it in MATLAB, it gave us an answer. It kind of spat out some results, but it also gave us this interesting warning message that appeared, which pop up in the terminal. So when you actually run that truss analysis script on this particular problem, you'll get something that says, warning, matrix is close to singular or badly scaled. Results may be inaccurate. Rcond equals 2.6 times e to the minus 18, and it occurs in truss elements at line 87. So what the heck is this? What the heck is matrix close to singular or badly scaled mean? It says our results may be inaccurate. So at least it's telling us that we can't necessarily believe what's coming out of it. And then it gives us Rcond equals 2.6 e to the minus 18. What does any of that mean? Any guesses or kind of intuition behind what you think that means? How do we interpret that? Any
Is the Rcond the value of determinant of the matrix?
Rcond actually is it's not the determinant, but it is related to a property of the matrix itself. Yeah. So I'll kind of go into the details. Is anybody familiar with the notion of a condition number for a matrix? No. Okay, good. So today we're going to explain that. So we're going to figure out what exactly this means, what all this kind of relates to, and kind of relate it back to the properties of matrices and what constitutes an invertible matrix. Really, Rcond is a way of assessing, how invertible is this matrix? And if you have an Rcond that's like very close to zero or close to machine precision, then you're in trouble. And that's kind of what Rcond is telling us in this case. Just kind of to give you the quick and dirty version. Yeah, go ahead.
Equal to zero, the matrix can be inverse equal.
Actually, it's the opposite. So if Rcond is zero, then it would basically imply that the matrix is singular or it's not invertible. Yeah, yeah. So it's kind of a proxy for the determinant, if you will. And a singular matrix is really one that is not invertible or one that has a zero determinant. So when it says this matrix is close to singular, really what it's saying is that the determinant is close to zero. It's not exactly zero. So it's trying to do it, but due to numerical precision and other kinds of issues, it's really questionable as to whether you should be inverting this matrix. So ultimately, that can lead to some badly scaled answers and kind of other inaccurate results. So that's kind of one way that you can interpret this just kind of visually. But we'll explain a little bit more detail on what all that means in a moment. But I want to consider a slightly different example maybe to explore that further. Suppose I had a slightly different structure. It's just two bars connected to each other, and supported through these pin constraints at the ends. So I'm constraining both the X and Y displacements at the ends of this kind of assembly. And this middle node, I'm actually kind of just applying a force, pushing it to the right. It looks kind of like a one-dimensional finite element problem in the sense that I'm kind of setting up like these two bars. They're collinear or parallel to one another, and I'm just applying forces only in the X direction. So essentially, I'm setting up this one-dimensional problem. And I could go through the same exercise and say, well, is this problem going to be stable? Can I uniquely solve for an answer just setting up this problem? I can count up the number of elements, constraints, nodes, and dimensions in the problem and do this inequality. And it turns out that, at least if I do that simple heuristic check, it tells me it should be stable. Okay, at least according to the heuristic, right? But what do you think? Do you think it's stable? I mean, would I be asking the question if it were? What do you think? I mean, assuming that maybe it's not stable, what could go wrong with this problem?
The middle node can move and down.
Yeah, it's possible that maybe this node could move up and down. I mean, physically though, if I had this setup, basically kind of like a cable that I'm fixing at the ends, it's kind of taut initially. would the cable want to displace up or down, assuming there's no gravity or anything like that that would displace it relative to that configuration? Is there anything that would drive it to want to, displace up or down physically? Not really. I mean, it would want to stay perfectly straight. You would think if it tried to displace, it would kind of incur some internal tension, and that would help to restore it to its perfectly straight configuration. Okay. So, I mean, that intuitively, that's what should be the case. But what happens when I try to run my MATLAB analysis on this? Ah, well, I try it and it says matrix is singular. Oh, this time it's not just close to singular, it is singular to working precision. And it cites the same line in MATLAB in this truss elements line 87. Okay, so what the heck is going on? Let's actually take a look and see what's happening in truss elements line 87. Okay, so this is precisely the step that involves inverting our system of equations or inverting that kind of subportion of the stiffness matrix to solve for the displacement degrees of freedom, the unconstrained ones. Okay, so we're attempting to do this matrix inversion step. So clearly something is going wrong when we try to do that inversion. So inverting the stiffness matrix is producing this problem. And as I've kind of mentioned previously, it's related to the matrix not being invertible. So why not? Why is it not invertible? That's the question that we need to explore. And if our matrix analysis, program isn't cutting it, maybe we have to actually go back and break out the pen and paper and do this thing ourselves. So let's actually kind of step through this example and set up the system of equations and see what could be going wrong. I mean, if you're encountering problems like this, it's a good fallback, It's good to know how to do things yourself if things come to it. So let's actually go about trying to set up this problem, idealize, the problem in terms of, pin constraints, constraining these different displacement degrees of freedom at nodes 2 and 3. And you can kind of see I'm actually taking an interesting approach to labeling the nodes in this case. Rather than going 1, 2, 3, I'm actually starting 1 is the middle node, 2 is the left one, 3 is the rightmost one. That's really just for the sake of convenience, so I don't have to rearrange the rows and columns of my stiffness matrix later when I'm trying to do that partitioning. So it's really just kind of like a minor sub-optimization, if you like, in the problem-solving strategy. Okay. Otherwise, we just have a force in the x direction here. Maybe we have different material and cross-section properties assigned to each of these elements. Let's for the time being assume that all these things are the same. So A1 equals A2, E1 equals E2, L1 equals L2. You could assign different values, but in the end, it doesn't really matter for the sake of this analysis. Okay, so if we wanted to, we could go about assembling the stiffness matrix for this structure, noting that for a truss element, in general, we should have a stiffness matrix that looks like this. It's the 4x4 stiffness matrix. And we need to know something about the orientation vectors for each of these two elements. And obviously E, A, and L, all these properties that are, characteristic of the length and cross-section and material properties. Okay, so if we want to define the stiffness matrix, the truss element stiffness matrix for each of these two members, again, we need to determine what are the orientation vectors for these two elements. In this case, if we're trying to find a unit length vector aligned with, let's say, the axis of element 1, we could pick simply a vector that is aligned with the global x-axis. So in other words, a vector who has an x component equal to 1 and a y component equal to 0. And we could do the same thing also for element 2, because it's also oriented in a direction that's aligned with the global x-axis in this problem. So both of these orientation vectors for elements 1 and 2 are just, 1 and 0. Those are the two components. So we could plug them into these different entries of these transformation arrays and expand out this whole expression. Alternatively, you could kind of use that direct expression for the element stiffness matrix, which I'll briefly recall here, just so you have an alternative way of thinking about how you would set this up. For an element stiffness matrix, remember it's EA divided by L of, in variable entries, you might have cosine squared, sine times cosine, and sine squared. And all of these have plus signs. And if I wanted to, I could also say, this whole thing, we could call that some submatrix. It turns out that the form of this stiffness matrix kind of looks like these same arrays, basically just with minus signs on the off diagonal and plus signs on the main diagonal. That's it. And where cosine and sine are clearly cosine theta, that's technically lambda x, the x component of our orientation vector, and lambda y is sine theta. Or as I'm abbreviating it, C and S. All right, not too bad. Okay, so if we do this, we actually find that, if lambda y, or S in this case, is just 0, as we have for both of these elements, then the S's in these kind of arrays are just all going to be zeros. So we have sine times cosine, sine squared, sine times cosine. All those are going to be 0. The only thing that's left is the cosine squared. And cosine squared in this case is just 1. Okay. So that's why in the end, our element stiffness matrix looks like this. It's mostly zeros, and in these kind of upper left-hand corners of each of these subarrays, we just have plus or minus 1. And then this k hat E, I'm just abbreviating as EA divided by L. Okay, so both of our element stiffness matrices for elements 1 and 2 look like this. So now we can go about just kind of plugging them into the appropriate locations of the global stiffness matrix and taking our algorithmic approach to setting up and solving this problem. So as we discussed in the previous lecture, let's set up some blank array, dimension to be equal to the number of global degrees of freedom in our problem as a whole. In this case, 3 nodes and 2 degrees of freedom per node, assuming we haven't applied any constraints yet, means we have a 6 by 6 global stiffness matrix. So let's populate it all with zeros and then sum in the appropriate entries, the element stiffness matrix for element 1, which has nodes 1 and 2. Which means we're going to be summing entries into rows and columns 1 through 4, corresponding to these corresponding degrees of freedom associated with nodes 1 and 2. So we'll sum in those entries for element stiffness matrix number 1 into those corresponding entries. And then we do the same thing for element 2, except it relates to nodes 1 and 3. So we're dealing with rows and columns 1 and 2, and actually 5 and 6. So that's why in our second step, when we sum the entries corresponding to the stiffness matrix contributions for the element stiffness matrix of element 2, they get summed into these corresponding locations. So we have only this 1 degree of freedom that kind of has some contributions from both elements, and the other ones are kind of scattered throughout this mostly 0 array. And that's a little bit troubling. The sheer number of zeros here, we like having zeros. We like having sparse matrices. But when you have a lot of zeros like this, that's when you should probably start to be worried. Something might not be invertible. Okay, so what happens when we go about trying to partition this into our subsystem of equations where we say really degrees of freedom for nodes 2 and 3, those are all going to be fully constrained. So we can say that these rows and columns, of course, corresponding to the degrees of freedom for nodes 2 and 3, we're going to partition those out and kind of throw them away for the time being. All we're going to concern ourselves with is the portion of the stiffness matrix related to the free degrees of freedom. So that's this upper left-hand portion of the stiffness matrix that really only has this one non-zero entry, K1 hat plus K2 hat, the two kind of EA divided by L contributions from elements 1 and 2. And otherwise, it's just this small 2 by 2 array, so a good candidate for doing some simple analysis on. Okay, so obviously this is a problem. You could kind of think, what's the determinant of this matrix? Clearly, yeah, it's 0. For a 2 by 2 matrix, the determinant formula is really just, the product of the diagonals minus the product of the off diagonals. So clearly the product of the diagonals is just 0 times this thing, so you get 0. And then the product of the off diagonals also 0, so the whole determinant's 0. So clearly we can't invert this stiffness matrix. And we could stop there, but why stop there? Well, there's a little bit more that I want to show in relation to this. Obviously, if I were to try to do this inversion, there is actually a direct formula for computing the inverse of a 2 by 2 matrix. It's as kind of what's shown here. If I have the entries of some 2 by 2 matrix A as A, B, C, and D, the inverse of this small 2 by 2 matrix is 1 divided by AD minus BC. In fact, AD minus BC is the determinant of this matrix, actually. Again, the product of the diagonals minus the product of the off diagonals. So we're dividing by the determinant when we're computing this matrix inverse. And then we're just kind of permuting the entries and maybe kind of turning the off diagonals with negative signs. This matrix actually has a special name. Does anybody know what the name of this matrix is?
Adjoint.
The adjoint matrix. Yeah, that's right. So the adjoint matrix multiplied by the inverse of the determinant is kind of a general kind of statement you can apply to the inverse of some matrix in general. And in fact, that's true for any size square matrix. You'll always have the formula being 1 over the determinant times the adjoint of that corresponding matrix. And for 2 by 2 matrices and 3 by 3 matrices, you can have direct formulas, but I don't think they're, yeah, I think you can do it for higher degree matrices, but it gets a lot more complicated. So in general, you don't end up computing the inverse of a matrix directly using this type of formula. Usually you use something more like Gaussian elimination or something like that, row reduction and all those strategies we talked about previously to actually solve a system of equations without explicitly computing the inverse. So it's a little bit of a subtlety, but knowing the inverse is helpful for doing some of these investigations. Anyway, so obviously it means if we're trying to compute the inverse of this thing, the adjoint is well defined. It's basically we're just taking the original entries and moving them around and maybe kind of assigning negative signs. It's when we take the, division by the determinant that things go awry. We can't divide by 0. And if we did try to divide by 0, then things would blow up, clearly. So that's a problem. All right, so, and this is exactly what's meant when MATLAB says that this matrix is singular. Really, it means it's not invertible, or in other words, the determinant is 0. There's a few different ways that you can say this. For some reason, all the mathematicians and everything came up with, variable language to describe the same thing. So singular matrices means not invertible. Anyway, yeah, who knows why they chose to kind of diversify the language there. So that's what's meant by this. But, if that's what means singular, what exactly is nearly singular? I mean, nearly singular, maybe it makes sense. The determinant's close to 0. So we're dividing by a number that's really close to 0. That can introduce problems. But in any case, I want to provide a slightly different perspective or a different definition of what a singular matrix might mean also. And I'm going to use something that will hopefully be useful to us later in the class. I'm going to talk about eigenvalues and eigenvectors. So anybody familiar with this concept of eigenvalues and eigenvectors? Maybe some kind of, it's kind of incongruous. There's some nodding and there's some head shaking. No, so I think it's probably worth the refresher for even those who claim to be familiar with the concept. So eigenvectors are this special vector that actually exhibits this property. Suppose I had a matrix, I'll just call it M. It's of size n by n. So generically sized, you could think of it as, a particular example is just think of it like a simple 2 by 2 matrix, like the one we're considering. Now, for this matrix, it turns out that there are a collection of vectors, which I'll denote V superscript I, indexed by I, where if I take this matrix and I do a matrix vector multiplication, I'll get a new vector that actually has the same orientation as the original vector, before I did this matrix multiplication. It's just scaled by this factor, which I'll call lambda. So really, these vectors, which satisfy this property, are sometimes called eigenvectors. And the scale factors that result from doing this matrix vector multiplication on an eigenvector, these are called the so-called eigenvalues. And really, that's all you need to know about this subject. I'll tell you a little bit more because I think it still has some relevance later on, like I said. One interesting property is that, for a given matrix of size n by n, there are a total of n of these different vectors that satisfy this property and n corresponding eigenvalues paired with them. So it turns out that also an interesting property is that each of these different eigenvectors are mutually orthogonal to one another. So in a 2-dimensional space, if I said, this vector is an eigenvector, it satisfies this property, and it has some corresponding eigenvalue, then I know that if there's some other eigenvector that satisfies this condition, it has to be perpendicular to that original eigenvector. So all of the eigenvectors basically have to point in totally different directions. They can't be at all aligned with one another. But they have to do so in sort of a generalized n-dimensional space. So, it applies in 2 dimensions, 3 dimensions, 10 dimensions, etc. So, generalize your conception of kind of like a vector space to include possibly n-dimensional vector spaces. It gets kind of funny. Anyway, so these eigenvectors satisfy this property. They're mutually orthogonal. So they have some of these other nice features. And if we take a look at our kind of representative stiffness matrix here, it's basically this matrix. 2 by 2 has these interests, right? And one of the eigenvectors of this matrix corresponds to just a vector that has entries 1 and 0. If you like, you can visualize this vector in a two-dimensional space as being a vector that's just pointing in like the x-coordinate direction, if you prefer. Anyway, so that's our kind of, first eigenvector. And the corresponding eigenvalue associated with this eigenvector, it turns out, is just equal to k1 plus k2. And you can verify that by saying, take this stiffness matrix, multiply it by v1. You'll get a new vector that has an entry that's non-zero in the first component and 0 in the second component. But the value of the second component is scaled by, k1 plus k2. So hence, lambda 1, or kind of the first eigenvalue associated with this eigenvector, is k1 plus k2. Similarly, we know that the second eigenvector has to be perpendicular to this first one. And if we do that, then we note that the second eigenvector, which points in kind of the global y direction, components 0 and 1, when we multiply this stiffness matrix times v2, we'll just get the 0 vector. So in other words, the eigenvalue associated with this particular eigenvector is 0, because it just scales that vector down to 0. Okay, so that's basics of eigenvectors and eigenvalues. Now, what's interesting about representing all these kind of eigenvectors and eigenvalues in relation to a particular matrix is that it's actually possible to represent this matrix in terms of its eigenvalues and eigenvectors. So by this formula, this expression actually tells me that I can assemble this matrix by summing together a bunch of smaller matrices that are contributed by each of the individual eigenvalues, and the eigenvector is kind of like taken in this vector outer product kind of representation. So V times V transpose is basically a vector times another vector flipped on its side. And ultimately, a vector times a vector in this format gives me actually a matrix. But it's a special type of matrix called a rank 1 matrix. It's basically formed by the product of these two vectors, and it kind of looks like this. So if I had V1 times V1 transpose, I'd get this matrix with 1, 0, 0, 0. V2 times V2 transpose would look like this, 0, 0, 0, 1. And if I wanted to assemble this matrix, I would just take the eigenvalues of each of those corresponding eigenvectors and then multiply them by each of these corresponding rank 1 matrices, sum them together, and you can verify that I actually recover the representation of the original matrix. So that's kind of one of the interesting properties of eigenvalues and eigenvectors, is that I can represent a matrix in terms of its eigenvalues and eigenvectors. And even more than that, if I wanted to know what's the inverse of this matrix, all I have to do is kind of take this expression and just flip the eigenvalues. So in other words, I could do essentially the same thing, but instead of using the eigenvalues in this summation, I use the reciprocal of each of the eigenvalues, and then I kind of plug them into this expression. Now, that works as long as all of the eigenvalues are not 0, right? So, I could do this, basically the same thing, except in this, rather than taking lambda 1, take 1 over lambda 1, and instead of 0, take 1 over 0. Now, clearly that's a problem in this case, because I can't take the reciprocal of 0. That would give me something that kind of blows up. I can, however, perhaps try to come up with an approximate representation of this inverse by supposing that if I had most of the eigenvalues being non-zero, maybe a few of them are 0, I could just say, well, forget about these extra terms in this expansion that involve, dividing by a 0 eigenvalue. And otherwise, just try to form the inverse, only considering these contributions coming from the non-zero eigenvalues. Now, if you do this, if you say neglect all the 0 eigenvalues and try to form an inverse in this fashion, you'll come up with something called a matrix pseudo-inverse. It's not exactly the true inverse by our original definition of a matrix inverse. It is kind of an approximation, or the best that we can do by basically saying just forget about these kind of 0 eigenvalues. Throw them away and try to form the inverse just in terms of these non-zero values. So it turns out actually MATLAB is doing this under the hood. If it encounters a matrix that has some of its eigenvalues being equal to 0, and if it has no hope of actually inverting that matrix properly, it will instead suffice to just use the matrix pseudo-inverse, and it will give you some results that kind of apply, K inverse times some vector, as we're doing in solving for the nodal displacements, using kind of just this first term, let's say, in that series expansion. So that's sort of an explanation for why we still got results. When we ran that problem involving that ill-constrained truss, it still gave us some results that looked kind of reasonable and would agree with what our intuition says. But ultimately, it's because MATLAB's doing some trickery. We didn't tell MATLAB to do this, but it kind of just tried anyways. It tried to give us an answer, and that's essentially what it was doing. So that's kind of a weird thing that MATLAB is doing some unexpected things, but it's good to know that it can do those things under the hood, and that sometimes it'll give you an answer, but you can't always believe it. Okay, so that's inverse matrices represented through kind of eigenvalue expansions and things like that. The other kind of cool thing that you can do with eigenvalues and eigenvectors is you can visualize different mode shapes of how the structure might deform according to these kind of eigenvectors. So the eigenvectors actually have another interpretation. The eigenvectors, you can think of them kind of like a particular mode of displacement or deformation that the structure might undergo. And you can associate it with that particular mode of deformation, a corresponding stiffness or a resistance to motion or deformation in that particular mode. So consider the first eigenvector in this case. For this matrix, it was exactly 1 and 0. Essentially, this corresponds in this reduced system of equations to effectively a displacement at node 1 in the x direction with unit magnitude and a 0 displacement in the y direction. So that's kind of visually being represented in this kind of diagram here. Node 1 is moving to the right with kind of unit magnitude corresponding to this kind of eigenvector representation, and there's 0 transverse displacement going on. Now, it turns out that the resistance to this particular mode of deformation corresponds to the eigenvalue associated with this eigenvector, or in other words, k1 plus k2. And that makes good sense because you have, this truss bar is resisting that kind of deformation of this node to the right, in the same way that this, truss node should be resisting it by pushing back against this motion. So really, it's the combination of the stiffnesses of both of these two bars that are preventing this node from moving. So hence, it turns out that the eigenvalues of the stiffness matrix have this kind of intuitive interpretation as being the stiffness associated with these particular modes of deformation as characterized by the eigenvalues of the stiffness, or the eigenvectors of the stiffness matrix. So that's kind of an interesting interpretation. And it also gives us some a way of interpreting what's going on with the 0 eigenvalue. So the second eigenvector, or the second mode of deformation that the structure might undergo, is this transverse deflection. So 0 displacement in the x direction, but unit displacement in the y direction at node 1. So it looks kind of like this. And according to our stiffness matrix, there's 0 stiffness associated with this mode of deformation because the eigenvalue of the stiffness matrix in that mode is 0. So what explains that? Clearly, we've rationalized that physically, we expect that if we were to set up this problem in real life, we took a cable or something like that, we pinned it at its ends. And then if we tried to actually displace the center of that cable upwards or downwards, it should technically resist that motion, right? There should be some non-zero stiffness associated with trying to push the cable away from a perfectly straight configuration. So why is it the case that the stiffness associated with this mode is 0? Well, yeah, that right. That's kind of the response I'd hoped. That it's yeah, it should be non-zero, right? I mean, intuitively, that's what I would think. It turns out that actually there's an issue that we came across in trying to formulate our truss element stiffness matrix. And it has to do with the assumption of small deformations. If we assume small deformations, then we're essentially saying that we're assuming that these elements are going to maintain their initial orientation even after maybe some displacement occurs at the nodes. What that means is that, even though the real deformation of the structure is going to look like this, according to how we've idealized our truss elements, those elements assume that they're going to stay perfectly aligned in this horizontal configuration. So even if we try to displace this node, transversely, these elements are never going to know that. They're never going to understand that, oh, once the displacement gets big enough, they should actually be elongating a little bit and becoming, put into a state of tension or something like that. But it's a flaw in the way that we've gone about formulating our problem and assuming small deformations. Most of the time, for most structures, that's not a problem. But if you have situations like this, that's where you kind of have to step actually into the realm of large deformations and introduce more complexity into the model. We'll talk about that more in the latter half of the class, and we'll actually formulate a form for the stiffness matrix that accommodates these potentially large deformations that could occur. But for now, just know that this is a limitation we have to work around. Okay, so finally, let's talk about the condition number. The thing that MATLAB told us was close to 0. Now, the condition number, can be interpreted in the context of the eigenvalues of this stiffness matrix. Supposing I have some matrix M, could be the stiffness matrix, just plug in K here. The condition number, sometimes denoted by kappa, is really taken as the ratio of the largest eigenvalue in that matrix divided by the smallest eigenvalue. Now, clearly, if one of those eigenvalues is 0, then you'll have 0 on this minimum eigenvalue, and it means you're going to be divided by 0. So you never actually typically want to report the condition number itself. It's better to report the reciprocal condition number, or RCOND, as MATLAB kind of abbreviates it. It's basically just take that condition number, flip it, and now you're putting the minimum eigenvalue on top, max on bottom, and in that way you ensure that if you're dealing with a reciprocal condition number of 0, it basically means one of your eigenvalues is 0. So in the context of interpreting RCOND, small eigenvalues basically mean, you're going to have one of the eigenvalues being close to 0, which means you can't invert your stiffness matrix. So that's what MATLAB means when it says RCOND close to 0. Now, a good question is, what if the member weren't perfectly straight? What if we kind of provided a little bit of inclination to these members? So if maybe there was a small angle that deviated it away from that perfectly straight configuration. You could go through the same exercise, assemble a stiffness matrix. I think this is very close to what you're going to be doing in homework assignment number 3, problem number 1. So I'll let you kind of work through the details here of setting this up and whatnot. But if you were to do this, set up this problem and assemble a stiffness matrix that's not necessarily, singular, the question becomes, how small do I need to make this angle so that I can actually render the stiffness matrix invertible? So in other words, if that angle of inclination of this member, theta, were really small, almost close to 0, do I still get this issue of, MATLAB telling me that I'm trying to invert like a 0 eigenvalue or something like that? And it turns out, at least it depends on the degree of precision you're working with in your computer. So let's suppose I chose theta equals 10 to the minus 9. It turns out you could work through, assembling this portion of the stiffness matrix in terms of cosine squared and sine squared. It turns out that, if you were to determine the reciprocal condition number, the ratio of the smallest eigenvalue to the largest eigenvalue, you could take that ratio, it would end up looking something like sine squared of theta divided by cosine squared of theta. And in the end, you could roughly approximate that under kind of the assumption of relatively small angles to something close to theta squared. So cosine squared of theta for small theta is close to 1, and sine squared of theta is close to theta squared. If that's the case, then taking 10 to the minus 9 for theta, squaring it, you get something close to 10 to the minus 18. And if I do this, if I set up that problem and I run MATLAB, it tells me the matrix is no longer singular. It says it's close to singular, badly scaled, etc. And it gives me an RCOND that's roughly the order of magnitude that I was expecting to see, e to the minus 18. And you could play around with this, try to increase theta more and more until eventually you get something maybe close to 10 to the minus 12 or so, 10 to the minus 8 or something. It'll probably still complain up until maybe you get past the threshold for machine precision or machine epsilon, which most of the time is close to like e to the minus 16 or something like that. Beyond that, now MATLAB's like, okay, it's within machine precision, as it says, and you could probably try inverting it and maybe it's fine. So that's kind of a subtlety that you can have structures that are not just singular. You can have structures that are nearly singular. So kind of like a nearly headless Nick joke, it could probably be thrown in there. Nearly singular. How can you be nearly singular? Well, like this. Anyway, the other thing that I'll throw out there is that if you were to try to run into this problem, or if you ran into this problem in the context of running like ETABS, SAP, ANSYS, all these different analysis software tools, you can still make the same kinds of errors in trying to set up and solve the problem. And they'll give you similar warning messages in somewhat different words, but essentially they all mean the same thing. You goofed. You made a mistake in setting up your problem. You should go back, try to make sure that you're supporting the structure correctly, or that it's not unstable in some way. So really, this is your signal that like it's trying to politely tell you that you did something wrong. So user error, in other words. But it really is important to understand that you can get yourself into trouble. Even though the tools, nominally, you can set up a problem in a certain way, it doesn't always mean that the analysis code has to give you an answer. Even though MATLAB tries to give you an answer, it probably shouldn't be giving you an answer. It should just stop and say this. It says, go back, fix it. You fix it. It shouldn't give you an answer. Anyway, so if you were to go through and do this, you could visualize what those kind of zero eigenvalue modes of deformation look like. For this ill-constrained problem, it looks like this. So this is the eigenmode, or kind of the eigenvector of deformations associated with that zero eigenvalue of this ill-constrained problem. And it correctly corresponds to this kind of rigid rotation of the structure. So kind of interesting. Anyway, I think that's all we have time for. If you have questions related to this, I have office hours immediately after class, so we can continue there. But otherwise, I'll see you on Monday.